And just so you know, that clock is an hour off. All right, start out with any questions on chapter 8. Any questions on 8 or 9?
Could you go over number 50 on chapter 9?
50 from chapter 9? Did you see the note that I wrote?
Yes,
Okay,
I think so.
and you still want, okay. I just didn't know if that would have answered the question. So the basic gist right there, and the strength. Oh, no, there is strength. All right, so 0.65 kilogram box, that's 0.3 meters from there to there. This is 0.5 meters. That's on distance D. That's 40 degrees. Slides on track down the hill, comes to rest at distance D from the base. Kinetic energy between the box and track is negligible. On the hill, with the coefficient. All right, so here, the coefficient of kinetic friction is 0.35. Here, the coefficient of kinetic friction is 0. And here, the coefficient of kinetic friction is 0.35. We have the spring constant of 34.5 newtons per meter. And it's compressed 30 centimeters with the box attached. And so the 30 centimeters is not just how far the box is from the edge of the cliff, but it's how far the thing has been compressed. And, all right, so finding D. Friction's involved, so we have non-conservative forces. Matter of fact, non-conservative work being done. So I know that the non-conservative work is equal to the change in energy, which is E final minus E initial, because that's what change is. So I have my initial energy plus the non-conservative work is equal to the final energy. What are my two types of energy? Oh, more general than that. Yeah, there's the two I'm looking for. All right, so we have initial kinetic plus initial potential plus the non-conservative work is equal to the final kinetic plus the final potential. Well, before we get to the questions that I know all of you are anxious to answer in unison, what potential energies are involved in this problem?
Gravitational.
You said
Gravitational.
oh, gravitational. Okay, so we have that one because weight's involved, and the other one
Elastic.
because we've got a spring involved. So we have two types of potential energy here. So we have kinetic initial plus U gravitational initial plus U spring or elastic initial plus non-conservative work is equal to K final plus UG final plus US final. Now at some point you can cut out some of these steps when you get more and more comfortable with it, and some of you are already there and some of you aren't yet. But that's okay, I'm still trying to just do it step by step and eliminate as we go. Now time for the formulas here. Formula for kinetic energy.
1/2 mv squared.
Formula for gravitational potential energy.
mgh.
Formula for elastic potential.
1/2 K delta x.
Squared. That's the initial. The non-conservative work, because the friction that's acting on it is going to be constant. Because if we look in the horizontal sections of it, we have weight acting down, normal force acting up, and then friction's acting back. Now up here, there's also going to be a spring force to the right, and down here there's not. But the friction depends upon the normal force, and the normal force is equal to the weight and magnitude in this case. So we'll have a constant friction force up there and down there. So this will end up being the friction force times the displacement equal to mgh final squared plus mgh final plus 1/2 k delta x final squared. Oh, that's it. All right, what can we get rid of?
Final spring tension.
Or final spring.
Yeah.
Yep.
Initial speed. Final speed.
Because it does come to a stop at the end.
Final height,
Why?
because you can set the bottom to be 0.
Okay. So there's no energy in this problem at all. So we've eliminated all the right-hand side, left-hand side. If H is equal to 0 down here, then up here, definitely there's some energy. Spring is coiled to begin with, and then we're gonna lose some stuff. So we end up with mgh initial plus 1/2 k delta x initial squared plus, well, at this point, I know that the friction is going to be opposite the direction of the displacement, both cases. So the dot product will be negative, minus the friction times the displacement. Well, it's going to be traveling 0.3 meters up here, and I'm just going to label that as Z. And then down here, D. So X plus D equals 0. Not X. Okay.
What about the friction in the bottom?
The friction in the bottom, that's where the D comes in. Technically, minus Fk times the friction up top minus Fk times the friction down below equal to 0. Because we lose energy in both places. And at this point, do we know everything except for D? Oh, we don't have the substitution piece. We have a formula for kinetic friction. So this becomes mgh plus 1/2 k delta x initial squared minus go ahead and factor it. And then in this particular case, y equals, we have mgh plus 1/2 k delta x I squared minus mu k m g. I guess I should keep them separate since I'm going to solve for d minus mu k m g d. And so now we know everything except for d. I think the textbook then goes ahead and does the equation here. So if we bring that over and divide, we get mgh minus, or plus 1/2 K delta X initial squared minus mu K mg divided by mu K mg.
UKMGZ.
See? Any other mistakes? And so, like a jog at this point, it's a math problem. So 0.65 times 9.8, we assume it takes place on Earth, times h. What is the height? The initial height?
0.5 sine 40 degrees. 0.5 times sine of 40 degrees.
Okay, I didn't hear sign when you said before.
That's like 0.31.
Plus 1/2 times 34.5, and that's one place where the answer key had a mistake. They said they dropped the decimal point. That's 0.3 squared minus 0.35 times 0.65 times 9.8 times 0.3, because it slides 0.3 meters. So 0.35 times 0.65 times. And you get some magical answer to that, just makes your life that much better.
They talk about like thermal energy and this, is that just, does that mean friction, pretty much?
Yeah, the thermal energy is sort of a catch-all that physics textbooks do. That still under this idea that energy is conserved. And so even though our box is losing energy, that energy has to go somewhere. And so that energy is going to go into, well, usually gets transferred into the kinetic energy of the at the surfaces. In other words, they heat up.
Mm-hmm.
So the box will get a little bit warmer, the ground will get a little bit warmer. And they just dump it into this thing called thermal energy. I think, if I recall correctly, they were dumping it all into the thermal energy of the box. In other words, the box was heating up, the ground wasn't. But I could be, my memory could be off on that. Well, actually, I was doing some work. Yeah, the ground is doing work on the box, so taking energy away from the box, or transferring it. Yeah, I don't think there's enough information to know how much the box would heat up versus how much the ground would heat up. Right, two of you started out asking about this problem. Was your question answered?
Yeah.
Okay.
The textbook has a different equation for this. It says that Ki plus U sub I plus total work equals K sub F plus U sub F plus the change in internal energy.
Oh.
Which is the friction part.
Right. They are taking this energy right here that the system is losing and saying it's just being turned into internal energy in the system. So where we have it losing energy in this form right here, but they have it on the right-hand side, gaining energy, gaining internal energy.
Yeah.
Yeah, it's mathematically the same. Other questions from chapter 8 or 9?
There is like a page that has a 1.8 in the explanation.
Yeah. Yeah, that's the one they, for whatever reason, there are two mistakes in the solution that were pointed out to me. They have this as 1.8 in the solution, and they have that as 345.
Okay.
Yeah, I put a note yesterday, at some point within the past couple days, I put a note, under the assignment. So if you printed it out before I posted it, then, yeah, there would be potentially some confusion there.
No, I was going forward and backward, what I missing here.
Yeah, part of me is surprised there's not more mistakes in the solution, Daniel, but then again, I only fix certain problems, so maybe there are. I just haven't seen it yet.
Not, and the last problem, the 79, the bungee thing.
Right.
The first part goes very, very good, and then there is a thing saying that the elastic constant change depending on the length.
Right.
And then it says just that it must be inversely proportional to the length.
Right.
And I don't see any like demonstration how to reach that. Let me see where it is. Thing is here.
I did that on Thursday, I just posted, yeah, I mean, too late for this, but I posted where I worked through the solution again a little bit more smoothly than I did in class on Thursday. So there is a post under the lectures from the semester where I basically took it, I cut out the mangling that I did on Thursday and I put it in a fresh section where I went over it. Obviously, not helping you right now, but, so,
For this one?
for that one.
Okay.
I didn't mean to stop your question, it's more of a, now you know. That hand gesture is the international hand gesture of rainbows.
Will you give, like, in the test, will you give us the equations for the non-conservative work and all those?
Yeah, I'm pretty sure it's there. Actually, well, people are thinking if they have any more questions, why don't I grab it and just confirm?
I wonder how that's gonna go.
And yes, I've got the 3 work energy formulas. All right, any more questions? Marisol?
It's concerning the master sets 8 and 9.
Yes.
I wanted to see if we could maybe get an extension of the class, just because a lot of us, I don't know about you guys, but I didn't have any Wi-Fi until yesterday, because of the power outages.
All right, thumbs up from the class. Is power outage a legitimate excuse for not doing physics? What are you proposing?
Just one class period, Tuesday, yeah?
Tuesday, 17th? Oh, wait a second, the 10th would be the next.
Yes.
Sure.
Great, thank you.
If it's ready Thursday, you may as well hand it in, but. Anything else? Pardon me, I don't want to do this in case it doesn't go out the way I expect it to, but I am curious about who would have given a thumbs down to Marisol. Just putting it out there as a thought experiment.
Did you have a power outage or no?
It blipped, that's all we had.
Why I went out for like 20 minutes and then come back on, so.
Yeah, I was even that long. We lost cable for about 10 minutes. That was the hardship we had to endure.
Oh, yeah, we didn't have, we lost power, like, I think the whole, like, where I live, our whole neighborhood was like without power until like Sunday. And, my job, we didn't even work because we didn't have power.
Wow. All right, so let's do this thing. One caveat. I went to go print it, right before class, I went to go print this, and I didn't have this quiz on the disk that I had here, so I quickly typed this out. So if there are typos, I will not be shocked. I think every word is spelled correctly, but other than that, if it seems like I'm missing a word, you might want to ask. And, you know, there's a question mark missing, I'm noticing right now. Sorry, only 2 questions, didn't give you more. Take one and pass. You are welcome. Anybody need to borrow a calculator?